Good
JP sir,
evening.
one more thing. I'm not able to.
So once again, I welcome all the MTech students and other students, those who are interested as a part of this course. So the title of the course has given Advanced Computational and Experimental Tools for Structural Engineering. So I welcome Mr. Prithvi, a research scholar from IIT Hyderabad. He is a PMRF fellow student. As a part of his PhD and further to program, he has to deliver certain hours of the course for the other colleges other than IIT Hyderabad. So for this reason, I'm requesting Mr. Prithvi to give your inputs to attain better knowledge and good knowledge in finite element modeling. The tool is going to use is ABAQUS. So I welcome Mr. Prithvi. You can start your presentation.
Yeah, thank you, sir. Just give me a minute. I'm just trying to share my screen.
Yeah, just a minute. Now you can share your windows.
Sure, sir. Give me a minute. Actually, there is some issue with my computer. Give me a minute.
Okay. Yeah. No.
No, okay. Let me just change my display settings. Yeah, what about now?
Still it is in the PPT mode only, not the presentation mode.
Even now?
Even now the same, no change.
Fine, I'll just remove this secondary screen. Yeah, what about now?
No change.
You can't see my slides?
We can see the slide only, the first slide, and it is not in the presentation mode.
Yeah, actually, I'm giving it as a presentation mode, but still I'm not able to.
No, I think when you are sharing, you have shared the PPT. Now you share the presentation.
Okay, maybe I'll just share my entire screen now. I think that
Entire
is
screen,
better, right?
that is
Yeah,
better.
I'll do that again. Now, what about now?
Yeah, now it is full screen.
Oh, okay, perfect. So before I start, I would like to thank the head of the department, Civil Engineering, MGIT, for kindly allowing me to deliver my lectures here for the PG students at MGIT. And I should specially thank JP sir for also kind of recommending my name to the HOD and also the other faculty members, Dr. Tarangini as well. So yeah, so with that, we'll start the lecture series. So this I have planned for like about 14 hours of series. So what I'll do is initially I'll just try to give some refresher kind of a course on FE. Like I think you already had covered the course FE in your MTech. Assuming that you have already covered it, I'll just touch upon some basic topics in finite element methods. Then we'll directly go into this software for finite element. So I'll be using ABAQUS. So we'll also have some introduction about the ABAQUS software, what all we can do using the ABAQUS software, and what, like, the GUI, the graphical user interface of this software. And then we'll also see some typical examples of what we can do using abacus and all stuff. That will be mostly I'll cover these many like whatever I have spoke these things in today's class. From tomorrow, I mean from the next classes onwards, we'll start with uh, hands-on training. So we'll start with basic, a simple 2D element kind of a problem. I mean 2D beam kind of a problem, and then we'll slowly go into slightly complicated models like RC beams, as well as if time permits, I'll also cover some kind of a beam column kind of a joint. So again, like JP sir has introduced me, I am a Prime Minister Fellow at IIT Hyderabad. I'm a PhD scholar and uh, in the structural engineering division. So, like he mentioned, as a part of my fellowship, I need to take some extra hours of teaching in any colleges nearby. So, as part of that, I was requesting the HOD for this, and he agreed, kind of to and allowed me to deliver these lectures. So few things, not these are not the rules, but you can stop me in between and you can keep asking me. And I don't think this course is this is any, you're not going to get any credits for this course. So this is open, so you can ask me any questions if you want, so that there is no fear of getting a bad grade or something like that. So please try to ask as many questions as possible, so that you can learn, as well as along the way I can also try to fine tune how I deliver my lectures. And I keep asking some questions. Please try to respond. If you're not comfortable responding by saying it loud, you can also message in the group, so that I'll also see that. So there, with that, I can kind of gauge what kind of knowledge you guys are having. Okay, so with this I'll start my presentation. So here I have given a different title. Actually, what JP sir was giving, that title was more that looks better than what I kind of given here. It's so obviously I'm giving some. I'm going to talk about computational tool, and that computational tool is Abacus here. So why do we use Abacus to again do the finite element analysis? So these are the contents, like I mentioned. Initially, I'll start to give some overview of finite element methods. So this is like a refresher, kind of a revision of what you already studied. And second one is directly we'll go to the introduction to the software. So this software is like unlike the CAD software which you might have some experience, like the AutoCAD or some AutoCAD, SketchUp, you have Revit, and you also have Solid Edge, SolidWorks. So this needs some kind of a prerequisite, right? So because see, those softwares are for you, the CAD software or others, you might you'll be using it to have some kind of to make some sketches, or to prepare some drawings or something like that. So there you may not need any prerequisite, except you need to understand what dimensions you actually wanted to sketch. But in this, you are actually analyzing something, right? So for this, you need some prerequisite, and those prerequisite are nothing but the finite element concepts. And like I mentioned, from next class onwards, like maybe subsequent classes onwards, will have an hands-on problem. So I'll start modeling, and you'll also start modeling along with me. uh, and that's how I'm planning to progress this lectures. So firstly, like what is finite element analysis? So uh, see, finite element analysis, it's again at the end it's again an engineering. It's like a method where to solve some engineering problems. So what kind of engineering problems, what all the methods do we have to solve engineering problems? So if we think about that, we have broadly, so far we have about, yeah, sorry. So broadly we have, first one is experimental methods. Second, we have analytical methods. Third, we have a FE method. Okay. So last, nowadays people are also bringing up machine learning and all stuff. Okay, but we'll keep it aside. We'll talk about this later. But first one is experimental methods. So what does experimental methods does? Like, if, like, for example, uh, let us take an example of a building. Okay, we have a 1 BHK kind of a building, and you wanted to design a building for certain kind of a loads. Okay, it's I'm just taking a frame structure, one single bay kind of a structure, and you want to design this column, you want to design this beam. Okay, so if you want to design these columns from the experimental method, what we'll be doing is we'll just kind of build this entire, we'll cast this entire column, we'll cast this entire beam, casting in the sense like you are making it physically. So let us say this beam is having a cross section of 200 by 200, and length, let us say it's a 3 meter span. So you'll cast this entire beam. Okay, and what are the loads coming onto the beam? Usually in a structure you will have live loads plus dead loads, plus, if we have several other loads like earthquake loads, wind loads, and all stuff. Right now I'm taking only a uh, you know some basic kind of loads which are live loads and dead loads. So you will load this entire beam, and then you will check for its ultimate capacity. What is the ultimate capacity? It's bending moment, ultimate bending moment resistance. How much the bending moment resistance does this beam have? So this is one kind of an, this is like, you are actually casting everything, and then you are testing it. That's an experimental method. So can we do this for every kind of a problem? Like, in future, if you want to go for a multi-storied building, so you can't completely test an entire building, right? So what happens is that experimental analysis is actually the truth, because it is correctly giving you what is actually going to happen in the real environment. It's exactly, it's the truth, the final truth. But it is most expensive, because you can't keep casting several buildings. You can't keep casting several beams, several columns, and all. For example, if you want to, let us say, a steel structure, if you want to construct a steel bridge, you can't test your entire bridge to, you just to design a bridge, right? So in that case, what happens is that this is the truth. So this gives you the right um, uh, right kind of an approach, but it is most expensive. So you can't keep doing this all the time. Okay, and analytical, next come, let us go to analytical. What happens to analytical is, so for analytical, usually analytical, analytical kind of a studies, we'll take use of physics, real physics, all the physics which we learned in our plus one plus two, as well as in engineering. We use that physics to develop some kind of an equation which almost or which tries to predict what is actually going to happen. So for example, in the beam cross section, usually when we are designing a beam cross section, first we'll assume that plane section remains plane. That means the strains across the beam are constant, linear. Strains across the beam are linear. These are the strain. This is my depth, okay, and this is my strain at the top tension side, and this is at the compression side. We'll assume that the strains from top fiber to the bottom fiber are linear, and then we'll propose this equation, which is called M by I flexure equation. M by I is equal to F by Y, that is nothing but V by R. Okay, from this we'll try to find out your moment resistance of different structures. Let us say, if you want to find out moment resistance, you will just try to find yield stress, let us say, for the steel beam, Fy into I by Y. If you know I, how do you know I? If you know the cross section area, sorry, cross section dimensions, you know I. With the cross section, you also know Y. And if it is a material, like for example, if it is a steel, you know Fy. So then you can simply find out what is Mr. Okay. So in this case, it is quite, there's nothing expense of it. There's only, you need to kind of use your basics properly. So here you are entirely using your physics. From physics, you are trying to derive, from physics, you're trying to assume something. So in this, the main assumption is plane section remaining plane. This is our main assumption. Okay. But from these assumptions, what we try to get is, we are trying to get this Mr. Okay. See, in this also we are trying to find out Mr, but in this we are trying to test entire beam. In this we had some assumptions, and then we are trying to find out what is Mr. Okay. At the end, we are trying to get what is our moment capacity or moment capacity of the beam. So this is not expensive because this there's nowhere you're bringing up a lot of resources here. Only thing is that you are trying to go back to the basics and fundamentals, and you're trying to understand the fundamental physics which is happening there, and then you're trying to postulate or you're trying to find out what is your MR or the moment of resistance here. Fine. I'm only taking MR here. You can also have shear force also, but right now for just time being, I'm taking bending moment. Okay. And then the third one comes is FE. What is FE analysis? So in FE, usually in analytical, we have something, physics which is playing into the picture. So in FE as well, we have, it's kind of a numerical method where you have some assumptions, numerical plus physics. Okay. So what usually we do is in FE, we'll try to, let us say you're having the same beam, you're having the same beam. So all the all the while, in experiment, it is again, like I mentioned, experiment is the ultimate truth. So you are able to find out what is the actual capacity of the beam. So this, let us keep it as the benchmark. Experiments has to be the benchmark. So in analytical, we had some assumptions, but physics driven assumptions. We had done some assumptions, and then the physics is actually trying to drive you to find out what is your moment capacity. But in FE, what happens is that the same beam in FE, what we'll do is we'll kind of break it into parts. We'll try to break this beam into several parts. And by now you would have guessed what these parts are. These parts are nothing but the elements. So you take one element out, okay? And then the element has different boundaries. You have one boundary over here, one boundary over here. Even these are boundaries, but these are traction-free boundaries for our right for current. I'm trying to, yeah, I'll show it here. So you have one boundary over here, another boundary over here, and this is uh, for this example. There's no loads or anything occurring on this, so these are traction free. So these two boundaries you have, and these boundaries, let us say you have u, which is deformations, and let us say this is of ux. So in the numerical methods, what you try to do is you'll try to assume what are the deformations happening first. So how do you assume? So we have several equations to assume it. What usually what we'll take is we'll take a linear assumption where we say that deformations are something like a plus bx. So from deformations, you'll find out strains. So let us say if it is a parabolic assumption, what are strains? Strains are nothing but du by dx, and these are nothing but 2bx plus c. From strains, you'll find out stresses. What are stresses when you have strains? How do you find out stress? Stress is nothing but epsilon x times Young's modulus, right? So I'm talking only about the linearity when we have a linear kind of a scenario. So once you find stress, you can find forces. How do you find the force? Force is nothing but stress times area of cross section. So once you know forces, you can know, like, you can, from forces you can find out, if you want moments, you can find moments. If you want shear force, you can find out shear force. So again, at the end, ultimately you are finding out your final demands which are going to come onto your structure. And here the assumptions are, you're assuming first, you'll try to assume that initially you're trying to assume some functions which are u of x, which is a plus b bx plus cx square, something like that. And then you are trying to differentiate it to find out strains, and then the strains are multiplied with Young's modulus to find stress. From stress, you are multiplying your area of cross section to find forces, and there you are again coming to conclusion that this is my MR. Okay. See, at the end, you actually wanted to find out what is the MR, but there are three different ways. One is again by testing, you got this MR. By analytical studies, where you are actually assuming something and then you are postulating something and then you are getting MR. And numerical methods, where you are actually starting to assume some equation for deformations, then you are ultimately finding out your MR. These are the three different types of methods where you can solve engineering problems. And again, by solving engineering problems, what do you mean by solving engineering problems? At the end, you wanted to know, you already have a demand, load demand. Okay, how do you know the load demand? Because let us say if it is a residential structure, you know what are the live loads going to come, and what are your live loads, what are your dead loads, everything. You have idea about that. And uh, and with those load demands, you also wanted to design the structure to to uh, design the structure to uh, withstand that live loads. And to design that, then you have these three different process to find out. So to conclude, what I wanted to say is, like, there are three kinds of methods. One is experimental, which is again the ultimate truth. The next one is numerical, and the next one is analytical, where you use physics, driven kind of a problem, but there are some assumptions even into it. Then third one is finite element methods, where you start with some assumptions in the functions, and then you will ultimately try to find out your uh, uh, final resistance of the structure. Okay. So, like I mentioned, this breaks down the complex structures into simpler parts. Like I mentioned, it's like, you will be breaking down into simpler parts, and then you'll find out the ultimate capacity of that structure. These are used in structural. So again, like, we are the structural engineers, so we do use it in structural engineering, in thermal, fluid, and other analysis. So thermal, fluid, mechanical, as well as the water resources people over here, right? They will also use this finite element analysis in their in the designs, as well as in their analysis. So uh, again, what are the applications of this finite element analysis? So, like, in the previous slide, I just missed out something. So uh, experiment methods are most expensive. That you have, I think you agree to what I said, because you need to keep on casting several specimens to just to find out the design capacities of them. That's waste of time, waste of money, as well, right? So for that, what happened is that, we'll try to assume something, and then we'll say that let us go for a conservative design. Not too much of conservative, but let us have some conservative design in this thing, so that at least it will sustain some kind of it will sustain the loads which are going to come. From that, we got an analytical solution. And then in finite element analysis, it's like, assuming something and then getting out of it. Finite element analysis actually has, when expense is concerned, finite element requires a lot of computational time or computational cost as well, because you need some not special computers, but you need a high processing computers, to analyze different problems using this finite element analysis. So these are used in structural analysis, like buildings, bridges, automotive parts, and stuff like that. Thermal analysis and other fields as well, biomechanics, aerospace, and material science as well. I'll just show some examples. So this you can see. You may ask, right? You may ask. See, we already have several other analysis softwares like StatPro. Okay, now here I'll just stop, and I need to ask some questions. So, yeah, how many of you are able to follow what I'm saying? I think I got some chat also. Yeah, you can message, or you can raise your hand, and you can tell me if you have any queries, or if you want to ask something.
Participants can unmute yourself and you can speak, no problem.
Okay, so I have a question. So, how many of you, what are the softwares most of you guys know? Like, you can mention anything from CAD, like AutoCAD, SCAD, ETABS, anything, you can please mention. You can message in the group if you. So, Raghu has something to say. He was saying that besides having force methods and displacement method, FEM is also another method to analyze the structure. Yeah, yeah, I agree. Yeah. STAD, ETABS, yeah, STAD, Revit, CAD, yeah, CAD, ETABS, STAD. Yes, See, so whatever I was telling about the stats of this Abacus software, the same thing. See, it's almost like looking similar to STAD, right? So why do we need to use Abacus? So that I'll try to explain. Okay. Yeah. Thank you for your responses. Yeah. Now I have some idea about what you guys are familiar with. See, in this, if you see, this is a beam column joint. Okay. This is a beam column joint. If you wanted to find, you can see these cracks here. These are the cracks. You can see these cracks. First thing, in STAD is definitely a very useful software where you and also ETABS. So where you will try to see or visualize reaction forces, like demands. Then you will try to understand what are the demands coming onto the structure, so that will be easy for you, and that will give you an input for the designs of your structures. So in this case, if I want to see this crack propagation, let us say this cracks, I think I just overwrote. Let me just clear this out so that you can see this cracks. So I hope you can see the cracks here. Let me zoom it. Yeah. See, you can see these cracks here, right? So there are several cracks coming onto this beam. And by the way, why the cracks are coming over here? Because see, this is a column, this is a beam, and you are applying a load. So this is actually called an actuator. So this actuator is applying this actuator is applying this actuator is applying force in this and in this direction. So this is like a cyclic load. So the force are coming upwards and downwards. It's trying to move this beam up and down. So these are the cracks which are formed on. You can see these cracks forming here. So why do the cracks are actually it started propagating from this end, because this is kind of a cantilever. It's a kind of cantilever, and you know that for the cantilever you have maximum moments at the support, right? So that's why the crack started coming from this place, and then slowly it started propagating in here also. Fine. So my question is, can you see such cracks in StatPro? We can't see that cracks, right? In StatPro, it only gives you what are your reaction forces, what are your bending moments, what are your displacements, and all stuff like that, right? So in if you wanted to see where the cracks are coming, so that can be done in StatPro, right? So that's where you use this Fidelman tools called Abacus, Abacus, where you try to understand how the crack is propagating, and why do we want to know why the crack is propagating. That we'll study in the further slides. See, now this video, you can see this video is actually this structure what you see here, right? It is a it is a 7 by 2 meters by 4.6 meters. This is a solar panel structure. Okay, this is a solar panel structure. So this is such a huge structure, first thing. Okay, and if you want to analyze this structure, see see, when I say analyze, what does it mean? Because you wanted to see what are the loads coming onto the structure. So again, going back to the basics of structural analysis. So what the structural analysis teaches? It teaches that what are the demands onto the structure. Okay, what are the demands? So what demands we have, the structure gives, it has loads coming onto the structure. From the loads, it gives moment demands. What are the maximum moments? What are the shear forces? So this is the part of structural analysis. So if you know this moment demands or the load demands, what you can do, you can then design. This is the next part of entire structural engineering. First, you will try to analyze the structure. You will try to find out what are the demands the structure is actually kind of giving as an input. If you know the demands of the structure, that means, let us say, if it is a simply supported beam. Okay, if it is simply supported beam and having a UDL of WL, uh, W kilonewton per meter. So what is the bending moment at what maximum bending moment? It is, I think it's WL squared by 8. So this is the demand that this beam is going to give. So you need to design this beam for this much of load demand, and that's where the design comes into the picture. So here you check it. So this is like 7.2 meter by 4.6 meter area wise. And can you use that structure for? Can you can you test that structure first of all? Like always because you can't test that for several times, right? So what you'll do is you'll test once, and then you'll have some demands. Let us say you'll test this. You'll try to test that structure once. So once what we'll do is we'll try to test this. So this solar panel we are trying to we what we try to do is we try to apply some wind loads. So uh, instead of wind loads, what we try to do is like we try to use a equivalent point loads kind of a system. Anyways, first we'll try to do an experiment on this structure. So experiment first, then let us say experiment gave me some result, which is the maximum resistance. Let us say the experiment gave us this much, some p value. Okay. Then what we'll do is the same thing we'll try to simulate in FE analysis. In FE analysis, we'll try to build the same structure. So what we'll do is first the same structure we'll try to model it. So this is something like this. This is also something like this. So we'll try to model the structure and we'll try to apply the loads on the structure, and we'll again find out what are the demands of the structure. Let us say MR equal to, this is P experimental. Let us say this is P FE. Okay. See, the model should actually replicate the correct experimental value. So P FE should be exactly equal to P experimental for an ideal condition. But again, like I said, this is an assumption, right? FE has several assumptions taken into consideration, and in experiments as well. See, when we say simply supported, see simply what does the simply supported means? Here you have a rotation, which you are allowing a rotation at the support. Here you are allowing a rotation at the support, and also you are allowing a translation at the support. Okay, we can easily say that this is simply supported, but when you are trying to do an experiment, you can't simply get a simply supported as similar to what you simply write it on a paper. It's very hard to get a simply supported experimentally, because this supports you are saying that it is laterally, it can move. Okay, but this support this beam has to stay on some support, right? So you have a friction between this beam and this roller. So that friction, because of the friction also, it kinds of not allows the structure to uh, kind of translate in this direction. So we have several assumptions in that case. So ideally what should happen is P FE should be equal to P experimental. Okay, this is the ideal condition, but because of several assumptions, P FE is actually not exactly equal to P experimental, but we can always have a margin. Okay, margin of error. So what we'll do is, let us say I'm okay with PFE being plus or minus 10 times of P experimental. Okay, this is like plus or minus. What I mean to say is, like, the difference between PFE and P experimental is plus or minus 10 times. That is also fine, right? Because I'm saving a lot of expense, a lot of cost by not testing it, and just I'm trying to get a estimate of my final capacities or my final movements here. So what we'll try to do is, like I mentioned, first we'll do an experiment and we'll simulate the same thing in finite elements, and we'll try to compare our experimental and finite results. If our finite element results are within, let us say, again, that is to the discretion of the user. Okay, if the user, like, if we are the users, so if the user is okay with 10% of error between your experimental and finite element values, then it's okay. There you are saving a lot of money. So in future, for example, if you have something else, in future you are getting a different kind of a solar panel. Right now, like I mentioned, this is a 4.2 by 7.2 by 4.6 meters. In future, you have 10 meter by 5 meter of panel. Here, now what happens is that no need to test this again. Test in the sense no need to do experiments again. Don't need to construct everything and do an experiment. Instead, what you can do is you can simply simulate this. You can again do a finite element study. You can simulate this. Okay, you can simulate the same thing, and you can find out your MR. This is PFE. And again, you should also know that this PFE will be P experiment plus or minus 10%. Okay. So what I try to tell what I try to tell you in this is that FE, whenever you do an FE analysis, you should always have some experimental validation to that. Okay. So first you will do an experiment, then you will simulate the same thing in finite elements. You'll try to validate the results. So what I mean by validation is, like I mentioned, you'll try to see how much MR you are getting in your PFE, I mean, in FE analysis, and what is your MR in your experiments. You'll try to compare. If those comparison is well within the limits, then you'll say that my FE model is validated against the experiments. Once the model is validated, you can keep on changing your parameters, and you can keep on doing several analysis for different kind of loading, even for different loadings, different for different boundary conditions, etc. By this, with one experiment or few experiments, you are trying to get a lot of database of different kind of scenarios or different kind of mechanisms or different kind of boundary conditions, etc. So that is one case, and next one is this one. As you can see, this is my. By the way, this is the experiments which I usually do at IIT. So this is an impact test. So you can see this bullet coming out of this barrel, right? There is this small projectile which is coming out of the barrel. So here we are actually doing a dry test. This is just coming out and it is going inside a sandbags over here. So if you want to do such kind of test, this is kind of a dangerous, because this bullet is coming at a here it is coming at a velocities of 20 meters per second. But in actual scenarios, you can also have projectiles or missiles shooting up into the skies at a speeds of 3 times Mach, or that is like 3 times the velocity of sound in air or something like that. So you can't test such kind of things always, right? So what we'll do is we'll do some experiments. Again, here also what we'll do is we have done some experiments here with this bullet kind of a system. So this barrel and bullet is coming out, hitting the structure here, and then we'll simulate the same thing in FE, and then we'll try to find out. We'll try to compare FE and experiments. If the comparison is well within the limits, like I mentioned, 10% or 5%, whatever, then we'll say that the finite element model is validated. And from that model, then we keep on doing several parameters. So let us say I have tested I have one experiment I have tested with a projectile speed of say 20 meters per second. Then what I can do is, like, once if I validate that experiment with this finite element model, then what I'll try to do is I'll keep on changing my parameters. Let us say if I want to know what happens if I shoot the bullet at, or shoot this projectile at 30 meters per second, 40 meters per second. So with this, for this, I don't want to do any test further. I'll just simply keep on changing my parameters in my FE model. So in FE model, I'll keep doing this parameters, and then I'll try to find what is happening into the structure. Okay. So this is the essence of doing finite elements. So usually we'll follow this kind of rule that first you do some tests and then validate your model with that test. Then you keep changing different parameters, and then then you can fine tune your model, and then you can keep on varying your parameters. Okay. So basic concepts, like I mentioned, I hope you are clear so far. Like you understood the gist. Can we compare coupon versus with the fee-based analysis? Stat for macro modeling and FER, or for micro and macro modeling? Yes. Yeah. Yeah. So yes, JB sir. I think, yeah, that's a good point. So what JB sir was trying to tell is, stat is for macro modeling. if you have an entire structure where you have you let us say it's complete building kind of structure, there you can, if you want to find out the reactions, and it's easy to find. In FEA it's a micro modeling, like you have a you can basically we can also do macro modeling in FEA as well, but yeah, that requires a lot of computational cost. But yes, I agree that FEA is for micro, like I mentioned, it's a member level kind of a models as well, and also macro modeling. And Raghu was asking me, can we compare coupon results with FEA based abacus analysis? What does it mean? Like, I didn't get the question, Raghu. Can you ask it clearly? Raghu, you can unmute and ask me. Hello, are you there? I think he left, right? Experimental coupon results validation with abacus results. See, fine. I think I'll answer to that question also, Raghu, because right now I can't directly jump into that. So, anyways, I have planned for coupon test results as well. But again, just to answer you shortly, what I can say is, like, in FE analysis, when you're analyzing, you should definitely give a material property to it, right? So, what material property are you going to give for that a model? So you are going to give a material property which you are going to get from the coupon test. So it's like, you are giving the same material property, and you're trying to get the same material property back, right? That's kind of weird, but fine. We can have a comparison. We can have a comparison for that as well. Others, are you able to follow what I was trying to tell? Okay, thank you. Yeah, thanks for your response. So we'll just go slightly. Yeah. Okay. I'll continue. So, like I mentioned again, this is again a refresher kind of a thing. So basically, FEA has these elements. So we'll break the structure. We'll break down the entire member into several segments, which we call it as elements. So that's actually called discretization, right? So we'll try to discretize the entire member into several elements, and whatever are connecting these elements are called the nodes. So these nodes, we have deformations. We'll assume deformation at these nodes. With the deformations, we'll find out the strains. How do you find out the strains? Like I mentioned, we'll differentiate the deformations. So differentiation again, du by dx, deformation divided by uh, length gives you the strain. From strains, you'll find out the stresses. How do you find that? You have a constitutive law. Constitutive law is nothing but the strain, how your strains are varying with the stress. For a linear element, for a linear kind of a coupon, or like linear kind of an element, it's like stress versus strain. Stress is equal to Young's modulus into the strain. So from there you'll find out stress, and from stress you can find out your forces. How do you find forces? Forces are nothing but the stress multiplied by area. Okay. So I think meshing is nothing but you are going to divide your entire elements or entire member into different numbers of elements. So that's nothing that's called meshing. Now, what are the different types of analysis you have? One is static analysis. So I'll just try to tell what are the analysis do we have. So first one is static analysis. So static analysis, what does it mean? Static means, see, generally there is no static, because see, static means it has to stay there. But usually what the loading which we have it. For example, we have a structure in big frame structure. Okay, and you have dead loads plus live loads acting onto the structure. Okay, why do you assume that these are static loads? So because dead loads usually it keeps growing up, right? Whenever you keep on increasing, let us say you have a beam and you have casted a slab onto that beam. So what happens is that while you are casting it, so slowly the load starts increasing. Slowly the loads on the beam starts increasing, and then it remains constant. So these are my loads versus time. So this is your casting time of your column. Let us say your slab. Slowly it increases. This is your this much is your casting time, and then after that it remains the same. Then slowly you are actually getting in your live loads. Live loads might be your benches or equipment, and also the also the also you also contribute to the live loads, right? So slowly after a certain time, then your live loads you keep on loading, and then the live loads come into the picture. So this will be your entire loading. This will be the maximum the loads which are acting onto the structure. So in this case, we are not we are not worried about your time. We are not worried about the time. So when you are not worried about the time, when the loads are when the load versus time doesn't matter, there it's called a static analysis. And why it should matter, why the load versus time should matter, I'll come to the next topic. It's called dynamic analysis. But that's places where you never experience the time effect. There it's nothing but it's a static analysis. So in all, mostly 95% of all our analysis usually are the static kind of an analysis. So usually, let us say, even in this building, if you want to buildings, columns, beam members, and like whatever, what different kind of loading. There we always use static analysis, and I'll also mention why. See where this static analysis comes into the picture. I'll also mention while I'm showing you about the software. That is about the static analysis. Next one is dynamic analysis. So dynamic analysis, here the time comes into the picture. So like I mentioned in my previous slide, see, see in this here it's a dynamic phenomenon. Once the loading time is very less, you don't even imagine the loading time in this case is about 10 milliseconds, less than 10 milliseconds actually. So in less than 10 milliseconds, your load has to spike up. So see, in less than 10 milliseconds, your load has to go up, and then it comes down, and then it remains constant. So in this case, is like in impact, sometimes in earthquake, because mostly earthquakes usually people do a uh, equivalent static kind of an analysis. But sometimes earthquake, if you want to actually simulate the real earthquake, you do this kind of thing. And in any kind of a blast phenomenon, also blast, when you have a blast kind of a loading, you'll also use this kind of a dynamic analysis. So again, how it is solved is also different, because I don't want to go much deeper into it. In static analysis, usually it uses Newton-Raphson scheme. So Newton-Raphson scheme, and in this it is mostly the force equilibrium. Static always tries to do a force equilibrium. What is a force equilibrium? Summation of forces is zero, and this is mostly this is again, yeah, summation of forces is zero. Dynamic, it has a different kind of an advanced schemes, which again you can also learn about these schemes. Similar to Newton-Raphson, you have several other schemes where it follows this something called a dynamic equilibrium. So what does dynamic equilibrium says? Dynamic equilibrium says that your forces as well as your accelerations should be zero. The summation of these things should be zero. So when a beam is actually, now let us say this is your beam. When you are hitting a beam with a load, let us say in my case, I told you, right, this is my projectile, it's coming and hitting a beam here. Once it hits the beam here, the beam also vibrates. You should understand that beam also vibrates. So beam vibrates, and you also have reactions coming here. And this also have some force acting. This is a contact force. And these are reaction forces, R1 plus R2. Beam also vibrating. See, what does beam vibration means? It's nothing but beam is oscillating, right? So the beam is oscillating to and fro like this and like this. So it is going like this and it's coming back like this. So it's like oscillating. In this scenario, what happens is that F contact, it's an algebraic sign. F contact plus R1 plus R2 plus the mass of my entire beam, okay, mass of my entire beam plus acceleration of each points on this. So each point will actually vibrate with different accelerations. That should be equal to zero. Okay. So in this we consider this dynamic equilibrium coming into the picture. So in this, mass plays an important role when you are considering a dynamic analysis. Fine, fine. See, we'll also see this when we are discussing about the software. But I'm just you just remember that we are mass is actually playing an important role in dynamic analysis and in force equilibrium. See, in force equilibrium also, what I mean to say is your forces are acting very slowly. Your forces are acting very slowly. That let us say your loading rate is u of t. U of t is small. Okay, what does u of t small? Then a of what is u of t is nothing but the velocity. A is nothing but acceleration. What is acceleration? Acceleration is nothing but differential of velocity. A of t is nothing but du by dt. When u of t is very small, a of t is also going to be very small. If a of t is very small, this part, which is summation of MIAI, let us say M is mass is, let us say, capital M, and summation of AI. So AI is going to be very small. If this is going to be very small, then M into very, very small quantity, which is almost zero, is nothing but zero. So that's where in static we don't consider dynamic mass into acceleration term, but in dynamic, as our accelerations are very significant, then we consider the acceleration terms. So then again, we also have thermal analysis. I think JP sir is actually having a very good idea about this thermal analysis. He does a lot of thermal kind of simulations in his research. So in thermal, again, what we'll try to do is, let us say in a fire scenario. So you have a building. In a building, let us say building caught fire, and let us say the fire is actually, it has caught fire here. What happens is that this member is going to fail, right? This member is going to fail because of fire on this structure. So we can also simulate this fire scenario in FE analysis. Okay. So in FE, we can try to give what are, see, fire is nothing but we can't actually give the fire. We can also, we'll try to give the temperatures, how the temperatures are varying in this column. Okay. What are the temperature gradient and what are the temperatures, what are the specific heat that can be given. And we can also find out what's going to happen to the structure. Okay. These are different types of analysis in FEA. Next, I'll stop here and I'll ask for, like, I'll just wait if you have some questions, or if you have, if you need some clarifications. Any questions or any clarifications? If you don't have anything, you can just simply say no also, because are you able to follow what I'm saying? Uh, so this answer is for the first question or the second question? Yeah. Okay. Yeah. Thanks. Thank you. What about others? Like, can anyone just simply say, like, you can write on the message, like, why do we do FE analysis? Just like, one or in one or two sentences, or you can unmute and you can tell me also. So what is the need for doing FE analysis? You can unmute and you can say, or you can write one or two sentences. For microanalysis as seen in which, yes, 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 yeah, yeah, yeah. Thank you, Burhan. Yeah. Anyone else? Yes. So can we do, yeah, optimizing? Yes, wonderful. So, like, one question, can we uh, see, like I mentioned, experiments are very expensive, right? So can we do FE without any experiments? Instead of going for testing all the elements, we can simulate the things in software and we can estimate the results here. Estimate the results. Yeah. Yes. Yes. That's right. And I think I hope at least yeah, most of you are able to. Yeah, most of you are able to. Uh, yeah, most of you are able to tell me like what's its what's the purpose of doing FE. So fine, I'll go ahead now. Is it okay? Yeah, I'll take that for okay. Then see, now we'll go to this software. Like I mentioned, see, so far I'm saying that we'll simulate, right? So what are we going to simulate and where are we going to simulate? So here we are going to simulate the same. Simulation is nothing but you are trying to replicate the actual scenario. That's what we call simulations, right? So if you're simulating something, that means that you have some data already, which is physical data. Like for example, if you want to have a uh, what do you call after as built plan, right? Like uh, if you are a practicing engineer, maybe you'll be knowing this. What does as built plan looks like? You already have a built up structure over there. You wanted to just replicate that structure in the form of drawings, right? So that's nothing but you're simulating the structure, or you're simulating the entire building, and you're trying to draw it in your piece of paper. So that's again a part of a simulation. So even here, when I say simulation, that means that you have a physical phenomena happening, and you want to see how is it going to happen uh, in your uh, in your laptop or in your computational tool, whatever you're using. So this is a powerful tool, definitely, for FE analysis. Apart from this, we also have ANSYS also. So it's also like ABAQUS, like ANSYS is also another software like ABAQUS, and it is known for complex and highly non-linear problems. See, non-linearity. Why do we? Why? See, if you are able to again brush up your learnings from Stat Pro. See, in Stat Pro, if you want to give any material properties, okay. See, in material properties, what material properties you are going to give? You are going to give yield stress, okay. Uh, I'm talking about the steel structures. So usually I'm a steel. Mostly I research on steel. That's why I directly go into steel. But anyways, FI is, you will try to give your FI. Let us say for my state, like, and you'll only give Young's modulus. What is your Young's modulus? It's 2 into 10 to the power 5 MPa. Fine. See, here it is material linearity, right? It's a linear kind of a scenario. You have a linear. Why I'm calling it linear? Because this is your stress, this is your strain, stress strain up to this much. That's it. This is your yield stress, and this is your yield strain. Stress versus strain. The slope of this curve is nothing but your Young's modulus. But if you have tested the if you have tested the coupon, or if you have tested the mild steel section, usually mild steel section will have something like this. It will have an upper yield, lower yield, and then small yielding, and then you'll have a strain hardening and then strain softening kind of a scenario. So you are actually not using this entire region of your stress strain curve in your uh, stat pro. You are only giving your yield stress as well as the Young's modulus. Okay. There is two types of non-linearities. One is material non-linearity. So this is material non-linear. Okay, where your stress versus strains are non-linear. These are some different other functions. And there is something. There's one is material non-linearity. Non-linearity. Second one is geometric non-linearity. See, what does geometric non-linearity means? So geometric non-linearity means. See, I think it's better for me to open a new slide and write it, because even I'm getting confused. Yeah, yeah, this should be better. I should have done this from the beginning. Yeah. So see, first one is geometric material nonlinearity. Material nonlinearity. Second one is geometric nonlinearity. Okay. Like I mentioned, material nonlinearity, like where you have a different kinds of. So let us say this is, you are only in some analysis you are only considering this portion, but what about this portion? This portion is being ignored in some analysis. So what does geometric nonlinearity mean? Geometric nonlinearity has several things, but I'll only discuss about one basic thing. Let us say this is a cantilever beam, and you are applying a force P. Okay. One assumption, if you remember in all our analysis in our undergraduate courses, one assumption is that we'll say that the material is linear and the deflections are finite. Okay, finite is like, that's a very strong term. We'll say that the deflections are finite. What does it means is, or finite and also very small. Sorry, it's not finite, it's very small and finite. So these deflections, whatever we are getting, these are very small. So when I say very small, it is very, very small when compared to the span. This is my span. Okay. See, when I'm saying it is very small, why do I say very small? Because I'll tell you something. So when your load is acting in this direction, let us say your beam has reached this position. So now your beam is in this position. Okay. See, in this position, your is your load still acting at this in this way or in this way? That depends, right? So it always depends. So in the basic fundamental assumptions, what we'll do is we'll say that even though if the load is acting in this way, we'll take it as in this direction, because we'll say that the loads are finite as the displacements are small. But let us say you are working on something which is very flexible. Sorry. Let us say you are working on something which is very flexible, where you have a loading scenario in this. Let us say it's almost in this direction, like this. It has almost the deflection was about very much comparative. It's almost, let us say, comparatively almost similar to L. Okay. So in this scenario, your load might happen in this direction, but usually what we'll simply say that the moments acting here is P into L. But in this scenario, that's not the case. Because in this scenario, what happens is that your moments will be, let us say this is theta. So this is P cos theta. This is P sin theta. Your moment will be PL times cos theta. And also you also have, okay, this is actually acting in this level. So let us say it's not. So we have reduction in your moment capacity, but you also have increase in your uh, increase in your increase in this in the forces in this direction. So here the geometric nonlinearity comes into the picture. So I think in stat pro we can also give, it also considers geometric nonlinearity, but in most of our analysis where we do all this building analysis and designs, we usually not switch on this part. But in steel structures, usually we'll also consider geometric nonlinearity in stat pro. These parts are actually being considered by default, or not by default. Actually, we need to switch on in ABAQUS. So even these kinds of geometrical nonlinearities as well as the geometric nonlinearities are being considered in ABAQUS. So that is what I wanted to mention here. When I say that uh, complex and highly nonlinear problem solving, this is what it's used, and commonly used in academia and industry. So definitely in research we'll be using it extensively, to understand the various effects of different parameters. Like I mentioned, I'll only test 20 meter per second velocity of impact. But what if the velocity of impact is 30 meters per second, 40 meters per second. We'll always go with simulations and we'll try to see what's happening with those simulations. And definitely in industry, in certain typical places, we definitely use this abacus as a tool for solving several industrial problems as well. So see here, so what I'll do is I'll keep on skipping to interfaces. So here, when I say key modules, like what all we have in Abacus, I'll open the Abacus software and then I'll show you. So what the first one is, I'll show the interface. This is. I hope you're able to see this Abacus screen also. What are the advantages of Abacus and situations? See, I think this is a very good question. So advantages we can't say. It's like it's see usually in ANSYS, what I see what I read and what I learned is that in ANSYS mostly it deals with uh, let us say if you have a thermal kind of a low thermal not thermal fluids kind of a analysis, or if you have a computational fluid dynamics kind of an analysis there, sorry, there usually people use ANSYS. In structures, actually, I haven't seen much differences between Abacus and ANSYS. So, like for example, one of my colleague uses ANSYS for impact testing, and I use Abacus for impact. We we both we both almost get similar kind of a output for our analysis. So I think it's there. I don't know. I think both are almost same. I think it's like yeah. I think that's a good point. I think both are almost the same. That I can say. But I think in thermal and in fluids, mostly in fluid dynamics, I have seen people using ANSYS extensively. Uh, but yeah, for structures, I think both are the same. It's about what you're more comfortable with. That's it. So we are more comfortable with Abacus because that's how most of our colleagues are kind of they also know mostly Abacus. So that's how we keep learning, and so that's why we started picking up Abacus. Any other questions? Abacus is more GUI friendly. Yeah, yes, I think JP sir is right. It is more GUI friendly. Yeah, correct. That's true. Any like shall I think you're able to see my screen. This Abacus software also, right? GUI. Yeah. Okay. Okay. See, uh, I'll just tell you one procedure, like one kind of a process which we usually do it in Abacus. So in Abacus, what the procedure is something like this. Let me tell you. Yeah. See, see. First thing, while we are doing simulation, what all the inputs which we want? Okay. First inputs. Let us say you want to simulate an RC beam or a steel beam only. Okay, just to make it simpler, let us say you want to simulate your. This is an I section. Okay. This doesn't look like a symmetric section, but please assume that this is a symmetric section. This is not there. Okay. So if you want to simulate this beam, what are the inputs that you need? First one is you should you should know the cross section details of this beam. Cross section details. Okay. Second one is what else you need to know? You need to know the span length, or the length of this beam. Okay, so these two corresponds to sketch. You need to sketch it, or you need to define a part. I'll tell you what is part, or what's a part, but these two comes under the sketching. So this is similar to what you do in CAD, or what you do in AutoCAD or Revit or Solid Edge, whatever. So you try to come up with this beam dimensions. You'll try to sketch this. So what we'll do is we'll have an input of this. Let us say this is ISMB, some ISMB. So this is say 140 and this is 300. I think this is ISMB 300 section. Yeah, I think this is ISMB 300. So this 300 and this is 140, and you have this thickness of the flange and the thickness of the web and the thickness of the flange. So then you also have your span length. Then you'll sketch it up. So you then first you do the model. Next, what is the further information you need? Third one is, first is the cross section details. Next one is the span length of the beam or column, whatever it is. Third one is material. Material. So what is the material property of this member? So like I mentioned, if it is a steel beam, then how stress versus strain? What are the different values of stress versus strain? Or if it is a concrete, then what are the compressive strength of this concrete and your strain profiles, etc. So these are the material properties that you also need. The fourth one is boundary condition. See, boundary condition is nothing but your support conditions. What are the support? So let us say if this beam is a simply supported beam, and I'm just giving a uh, line diagram of this. So this is a simply supported beam. So what we'll say is, at this end you have a pin support, at this end you have a roller support. So fourth one is you need the boundary conditions. So these are the inputs that you actually you should you should ask before going for. These are the basic inputs that you need to ask before you go for analysis in ABAQUS. First thing, what are the cross section details? What are the span length? Second one is, what are the material properties? And fourth one is, what are the boundary conditions? And obviously, see, in boundary conditions itself, you'll also get the loading conditions. So loading is nothing but, see, again, usually people think that some boundary conditions are again different to the loading condition, but loading is nothing but it's also a boundary. Like, you are applying some kind of a loads at the boundaries, right? So it's also like it also comes under the boundary conditions, the loading aspect also. Fine. So these are your inputs and outputs. So what outputs you need from this? First output is, you want again the same similar kind of thing. So you want moments, you want deflections, you want, what else you want? You want moments, deflections, you want shear force, you want stress concentrations, you want to see stresses as well, you want to see strains as well. What are the strains? You can also get a uh, small movie, like, movie in the sense, like, you also get an analysis movie in terms of video format. With this, what you'll do then, see, from the outputs, what you'll do then, from output, you can give a decision, you can get a decision for designing. Okay, so this you need to always ask for. So whenever you have a question about find elements, first you think whether is there enough, what do you call it, enough inputs available. One, the cross section dimensions, span length, material properties, and boundaries. Next, coming to the procedure. So that's what I wanted to show. So like I mentioned, sorry. So here, as you see, cross section and span length. Okay, what happens to the cross section and span length? See, first part, if you remember, it's cross section and span length. So how do I like where do I make utilize of those cross section, utilize those cross section and span length? That comes in this part which is called part. Again, it's part. So it says a create part. In create part, here you can create it. So I'm just showing some examples. See, this is again like a AutoCAD. It's like AutoCAD or like a Solid Edge or anything. It's like a it's like a it's an interface where you can create the sketch. So here you can draw your I beams, rectangular beam. Like for example, I'll just draw a rectangular beam. So this is a rectangular beam. I just draw a rectangular beam. You can give different dimensions, whatever dimensions you want, and then you can also give your span lengths and etc. Okay, so this is about your first input, which is sketching or giving the cross sectional details. What is your second input? Second input is nothing but the material properties. Fine. So material properties where how do you give your material properties? So for that, you can see this module over here. You can go to this property. Second one is property. Yes. See here you can see this part. In this property, you can always define your. I'm just showing it here today, but tomorrow we'll do a hands-on thing. Okay. I'm just showing it how to. So here elastic, you can give your Young's modulus. You can also give your Poisson's ratio. And like I mentioned, you can also give your stress strain, stress versus strain as well. So here you can see yield stress, plastic strain. You can keep giving multiple yield stress, plastic strain, different for different yield stress you'll get a different plastic strain, right? You can give that. So here you can input your material properties first thing. And what is your third one? The other one is the boundary conditions. So once you do this, then you can go directly into this loading and then you can give your boundary conditions, which I'll be explaining it, in the subsequent classes. So again, just I'll repeat what I was telling. So first inputs which you need to ask is cross section details, span length. Second one is material properties. Third one is boundary conditions. Next, the process is like, these are the inputs, but when it comes to the process of analyzing, so coming to the process, let us say you have given these inputs. Let us say your inputs are already being given. Now inputs are done. Next is once you get a beam or once you have done a part of the beam, then like I mentioned in FE, the major part of FE is discretization. Okay, what is discretization? Is nothing but you are breaking down this entire beam into multiple parts, and you are actually trying to multiple parts, and you're only trying to see what is happening with each part, and then you're trying to combine each parts together ultimate or the behavior of an ultimate or behavior of a full beam. So FE here it is a discretizer. You're trying to discretize the model. For discretization, like I mentioned, once you are, let us say in the previous example, you have given the cross section. You also know the span length. Now there is something called meshing. What you will do is in meshing, you will say, let us say this length of the beam is say 1000 mm, which is 1 meter. In meshing, you can say that I want this beam to be discretized into say 10 parts, 30 parts, 40 parts, 100 parts, whatever you wish. But again, we'll also come to the rules of meshing later on. But for time being, let us say that you can do it into n different parts. N parts. Okay. So let us say I want to break this down into 100 parts. There you will do a 100. You'll take it as number of elements as 100, and then you will break it down into 100 parts. So this is nothing but the meshing. So this you'll be doing it. Then you will also then you'll also then you'll also what is the next one? Yeah, and then you'll also give what kind of analysis you want. Is it a static analysis or it's a dynamic analysis? And there are several other analysis as well that I'll come to that when I'm showing you about different analysis. So this is also something which you need to give before you running your analysis. So let us say your problem doesn't have any time dependent kind of a loading, like impact blast or earthquake kind of a load. Then you'll go for a static kind of a load. Or for example, in my case, if you have an impact kind of a load, then you'll go for a dynamic load. So it's like a ticking. You just mark it whether it's a static load or it's a dynamic kind of analysis. So once you give all these things, so I'm just again repeating it. Uh, Hope you don't feel bored. So first one is you gave cross section details. Second one is you gave material details. Third one is you have given a boundary conditions. Fourth one, you have meshed. Okay, meshing. Fifth one is type of analysis. Is it static or dynamic? So once you do all these things, you are almost ready to go for your analysis. Like you can run the analysis. Then what you will do is you will run the analysis. Then you can visualize the different results. Okay, I'll show you the visualization and all the other things also. So see that again, I'm just this is again in terms of PPT. First thing is defining pre-processing. First, you define your geometry, materials, and you mesh it. Run. So which kind of analysis you want, you will run the analysis and you will try to define your model, which has been defined in the model. Then post processing. So these are the workflow in your ABAQUS. Define, run it, and then you visualize your results. Okay. So like I mentioned, this is your geometry. I'll show it in the software also. Let me show that in software. So first thing, you will sketch your model in this module called part. Second, properties. You'll go to properties, and you will input your material properties in this. Uh, I know you'll be curious to know what all these other icons are. We'll try to see like what all those icons. For time being, just keep your focus on to this tab here only module, which is property. Assembly we'll see tomorrow, because now I think if I tell it, it will not be you may not understand what I'm saying. So in the step, like I mentioned, right, static or dynamic, here is where you will give, see, this is static general, which is nothing but the static, and you have dynamic explicit and dynamic implicit. So this is where you give a dynamic explicit or a dynamic implicit kind of that is what which I was mentioning, dynamic and static. So then you have interactions. Again, this I'll tell you when we are doing hands-on problem. In load, we have the boundary condition. So see, this is boundary conditions. This is where you define your boundary conditions, create boundary conditions. What is the other part I was mentioning? I was mentioning about meshing. So in this meshing, see, you see this, right? So you see these dots. What does these dots mean? This is like your discretization. You are discretizing your beam and you are making it as a mesh. Then you go, there is this part called job. There you'll go and you will run the model which you have built, and then you'll see the results in visualization. I think this you are able to relate to your stat pro. In stat pro also, once your model is done, what you basically do, there will be some run option over somewhere here, and then you'll press to that run option. I think the analysis will be done. You'll get a pop-up saying that the analysis is over. Then you'll go to visualization or post processing, where it is called post processing, and then you'll see what are the results of your analysis. Okay, so I'll just show one example where, yeah, see, again, this is again the same repetition of what I mentioned. Material properties like elasticity, density, and all, assign materials to this model. Then you have different. Uh, Coming to material model, we can speak about this in the subsequent classes. So we'll be meshing it. Mesh quality is critical. Why mesh quality is critical? We'll do a simple example and we'll see, like, why mesh quality is critical. And we have different, I think you have studied about the solid elements, shell elements, 1D elements and beam elements, etc. So we'll use an appropriate element type there. And yeah, finer mesh improves accuracy but improves computation. That even this we'll have a comparison. We can have a comparison here in our next class. Like, we'll make a comparison about this. Why mesh quality is critical and also finer mesh, right? And like I mentioned, boundary conditions, you will apply different forces, fixed conditions, and these things, which almost ensures the realistic simulations. And different analysis type, like I mentioned, static, dynamic, thermal, and yeah, allows sequential kind of loading. Anyways, this is again a repetition of what I have said. Interactions and constraints. So we'll see about this. I can tell about this right now, but this will not be more. This will not make sense if I tell just just like that without doing any model. So we can just we'll keep this when we are doing the modeling. I'll explain about these interactions. Running a simulation. I'll show this is my post processing. So you can see this post processing. This is again a this is a column. This is a column. You might think why the column is horizontal, because I just put it in this horizontal mode. But anyways, this is a column which I'm working on. So you can see this entire part is a projectile or a missile. So this is a missile which is coming and hitting this column. You can see how you can visualize that thing also, right? You will get different contours. So these are your stress contours. If you see at the point of contact, you can see there's a lot of red colors which are coming, right? Red means like it's having a higher stresses over here. And see, interestingly, you can also see stresses red coming in the supports also. See, red initially when during impact, you can see red over here as well as here. See, you can see it here. That means at the supports also you have maximum stresses coming, and also at the point of loading you have maximum stresses coming. So these kind of visualization can happen, is possible using ABAQUS. Here I have only plotted strains. Sorry, these are stresses. You can also plot your displacements, how much see, you can see this beam vibrating also, right? See, it is going to and fro. If you closely look into this, you can see the beam vibrating to and fro, back and forth, up and down, up and down. So yeah, these minute details also can be captured using this software. So here I here I have only used my stresses as my visualization thing, but you can always have different kinds of things. If you want to have forces acting, you can. If you want to have displacements on the structure, if you want to have strains in the structure, if you want to have let us say strain rates, and if you want to have damage in the structure, you can always have this visualization tab coming handy for that. So see, you can extract results like stress. You can also analyze results at critical locations. See, for example, in my previous thing, my critical location is nothing but this part. Okay. See, my critical location is nothing but this part in this zone. What I'll do is I'll just take out this zone and I'll also analyze, like, what's happening there. Instead of all the other parts, I'll just take simple this cross section and I'll see how, when the load is acting, how this part is behaving. And what do we see again at the end? At the end of all this analysis, what we actually wanted is, what are your critical loads? What are your loads that are you going to see on your structure? Because if you have that idea, you can have a better designing. Yeah, you can have a better design, optimized design, and also you can save a lot of cost, and also you can save a lot of material aspect. So advantages again, it is definitely high accuracy when you have a complex models. So like I mentioned, crack propagation or impact kind of scenario, you can always use this kind of model for these complex scenarios. And limitations, see, it requires definitely it requires computational intensive. And I should not say this is a limitation. It requires prior knowledge of FE, because see, whenever you are doing some, let us say when you're saying meshing or when you are saying material properties or when you're giving inputs, these are your inputs, right? So your end results are going to be affected a lot with your inputs. Like previously, I was mentioning about what are your inputs. If you see our inputs, what are our inputs? Inputs are cross-section details, material properties, boundary conditions. See, cross-section details, material properties, boundary conditions, meshing, type of meshing, and type of analysis. So your end results are going to be influenced a lot by these inputs. So your inputs has to be as strong as possible, as right as possible. Okay. So let us say instead of giving some material properties, you are given some other material properties, then your model is not going to be perfect as like like what you want it to be. And even boundary conditions. Let us say if you have a simply supported conditions and but you have given some other conditions and then your results are going to be highly significantly different from what you actually expected. So this actually requires a very prior knowledge of inputs. And inputs that definitely means your finite elements. You should also have some knowledge on your finite element uh, schemes and even meshing. See, meshing is a part of finite elements. So how do we find out the optimal mesh size and optimal mesh size? We can do a mesh convergence that again I'll discuss when we are doing a hands-on training. So see again, like I mentioned, this is again we have several assumptions which we are having, which we are considering in FE models, right? So uh, see, more the assumptions, or let us say it's higher the assumptions, lesser accuracy, lesser the accuracy what we are going to get in the final results. So uh, again, that's like a balance between your assumptions and your accuracy. If you're okay with your some kind of accuracy, let us say plus or minus 10, you're okay with to go for some assumptions. But you want it to be a perfect match. I don't think perfect match is very difficult to obtain, but if you still wanted to have a perfect match, then your assumptions has to be as solid as possible, as less as possible. Again, these are the practical tips for the beginners. Usually, we can have we can start with simpler models, like I mentioned, and uh, the material properties and units. So, see, in StatPro, you can always say it, whether it is an SI unit or a FPS unit or you can give your own unit, like not your own, but you can customize your units, right? But in interesting in Abacus, it's not like that. You have to be unit consistent. So your units has to be consistent throughout it. Let us say if you're giving your units in terms of, let us say in length it's mm, and in stress, let us say it's Newton per mm square. In forces it's Newton. Then your results are going to come in terms of Newton mm. For moments or for shear force, it's going to be Newton, and for deflections, it's going to be mm. So it's like you have to be consistent from the beginning. There is nowhere where you can click or check the units. So it all starts from your from the time where you are inputting your units. So let us say if you wanted to give your units in terms of meters, then it has to be everything has to be consistent with meters. So if you are saying it's meters, right? So then your stresses should be in terms of Newton per meter or kilonewton per meter. Sorry, kilonewton per meter square or Newton per meter square. So that consistency again we can check while we are giving the models. Then we can critically ensure some accuracy and also validate the model with some experiments. Uh, I think this is actually what I have planned for today. And few questions which I have to you is first thing is how many of you have installed Abacus on your laptops? Uh, Hello, can you hear me? Okay, what about others? How many of you have installed at least? Burhan, do you like you tried installing or not? Like, or you have any issues while installing? Okay. Yeah, see, please install it because see, installation. You try to install it and you see if there is any issues while installing. Because I wanted this to be a hands-on session. It's like you should also parallelly model it and analyze it. Only then we'll try to see. Only then the benefit will be mutual because you will also learn something and even I will also try to gain something from this. Otherwise, it will be like a one-sided kind of a thing. Then uh, that will not be more effective because I don't even like that because I don't want it to be a one. I will install by tomorrow. Yeah, yeah, sure. What about others? I think others. So there's like one, two, three. I think four members. I think four. Yeah, four students have. They said that they'll install it tomorrow. What about others?
Right? Students have responded. Uh, Today morning, I have given one link for the to download the software. So in that page only, you will. I mean, there is one option how to install. You can see one video after downloading it. Just you follow that video to install in your system. So you try to understand the step-by-step procedure. uh, just to follow that video and you can install in your system. So unless until you install that, it is not possible to work on this software.
Yeah, yes, yeah. Please install it because I request you all to please install this. Uh, Let us have some hands-on only. Yes, because see this software also. Just this is again out of the topic. So see this software also adds up. Once you know this software, it also kind of adds up your CV as well. When you because now if you want to, I think most of you are planning to go for industry, right? So this will also add up to your CVs as well because masters usually people try to masters usually people if you have a master degree people try to see that you have some knowledge on these softwares. Stat and ETAPs are excellent there's no doubt, but if you have some extra, this will also give you some extra added edge with other when compared to others as well. So I sincerely request you guys to download this uh, and be ready for the subsequent classes. So in subsequent classes, we'll directly start with hands-on training. Before that, yeah, any questions so far? Questions, queries, or some clarifications or some feedback if you want to give. Anyways, I have some feedback link also. If you don't want to give it openly, you can also give me a feedback by sharing. Sir, is it also helpful for undergraduate students? Yes, yes, it is also. It is also helpful. Yes.
Yeah, one good thing is even if you don't know the fundamentals of FEA, you will be able to work on abacus just to by understanding some of the least concepts.
Yes.
So that is the main advantage of going with graphical user interface.
Yes.
But if you understand finite element thoroughly, then you will enjoy the background how it is working.
Yes.
Just one announcement I would like to give, Sir, with your permission.
Sure, sure.
Yeah, actually, Prithvi sir is going to take about 14 to 18 hours of class even after the 31st August also. I request him to take two, three more classes so that we'll finish around uh, 18 hours of classes on Abacus. So then I would like to continue the training maybe by adopting some other software, maybe statistical software. I will try to request some other faculty to take up these training sessions further. So that our planning is we would like to continue this training for 30 to 35 hours. So,
Oh,
and at the end of the training, I am proposing, to give one certificate for all the participants with the permission of HOD. So anyway, that I will communicate further. And even undergraduate students, I think only one student have joined. And if other students are willing to join, they can join. Yeah,
yeah.
that is what it is. Anybody would like to speak, they can speak. You can unmute yourself and you can speak.
Any questions if you have, or you want some clarifications, or uh, some feedback, comments, queries? I'm also fine if you. This is my this is feedback. You can also uh, open this link and give your feedback. If you don't want to give it openly, you want to give, you can view that feedback in that document. So please try to give a very what do you call, honest feedback, okay? Because that also helps me understanding, helps me to understand what you are actually want, what you guys actually want, and if there is, if there is any drawback from my side, I'll try to correct it, and then I can also try to I can also try to give an effective way of teaching from the next class onwards.
So by
Some,
tomorrow, everyone have to install the software and come prepared.
yeah. Before we leave, like, I have one last slide. See, again, I was telling you, right, why the purpose of doing final element analysis, right? I'll just give you a real life example. These are some of my like the experiments which I do. See, here there is a column member. You can see this is a sorry, just give me a second. Yeah. See, this is a column, okay, and you have a barrel, and I'll just switch on the video. You'll see what happens. It's very fast, I guess, but you can see it again. You see the barrel, the projectile is coming and hitting a structure here. You can see again. See, you can see the high speed. This is a high speed camera. The same thing. I captured the same event in high speed camera. 10,000 frames per second. You can see it comes, it hits the column, and it goes back. This is another scenario. This is another scenario. You can see it came and hit. It went back. You see here. It came, it hit, and it went. Same kind of thing in high speed camera. You can see this. See, the cost of doing such experiments is, it's very high. First thing. Second, it's risky because you are dealing with something which is coming out with a higher velocity, and the projectile which we are using is about 26.5 kg. You just imagine that much of mass coming and hitting some structure. That's risky. It's it's highly expensive. So what we'll do is, instead of doing several experiments of such kind, we'll do few experiments, and then we'll simulate the same thing in Abacus, and then we'll try to match those results, Abacus results, with experiments. And at the end, what we'll try to do is we'll try to keep on changing the parameters so that we can also kind of minimize our costs, as well as we can also maximize our benefit. All right. So yeah, this is one real thing which I was doing, so that's why I wanted to share here. Yeah, this is a feedback thing. Anyways, I have shared the link also, but my request is try to be as honest as possible. Please try to give me honest feedback. You can also scan this to give me a feedback. And from tomorrow onwards, I'll just give you a glimpse of the problems which we are going to do from tomorrow. So this is one-dimensional beam problem, simple problem. Beam, you have UDL and then you have a point load. Then we'll do analysis and see how what are the results from this. One thing also what we'll do is we'll also do a hand calculation. Simple. This is a very simple beam, right? It's a determinant beam. We'll also do a hand calculations and see whether our analysis, our FE results and hand calculated results are matching or not. That should match, but just for out of curiosity, we'll try to see. And then maybe one I beam, steel beam with similar kind of load, and then maybe this is another. We can also do a coupon. See, usually I hope you know why we use a coupon. So coupons are nothing but we cut out the material in this shape, dog bone shape, and then we'll apply tensile forces and we'll see the stress strain curve. We'll develop this stress strain curves. So this is how a stress strain curve usually looks like. Stress versus strain in linear portion, slide yielding, and then strain hardening, and then strain softening. Okay, so maybe we can also simulate the same thing. And this is the beam column joint which I'm talking about. And this is the RC beam. So we have a RC beam with reinforcements. You can see these red lines are the reinforcement. We can also try to simulate this, and we'll also see how this RC beam is actually, what are the results, or how this is how is this performing, and what are the outputs of this outputs from this beam. Okay, anything else if you want to tell, you can, all the students will provide the feedback. Yes, yeah.
So Prithvi sir, when you are, that RC beam, no? So
Yeah.
just you explain them how the damage that parameters can be calculated.
Okay, sure.
So
Yes.
that from the experimental results are the known model,
Yeah,
so they will get understand the damage thing.
sure. Yes, yeah. Yes, the inputs. So what JP sir is mentioning is he's asking how the inputs are. Like I mentioned in my analysis, in my presentation, I was showing you, right. What are the inputs of five elements? First one is cross section details. Second one is material properties. Third one is boundary condition. So how the material properties are actually generated. So that's what he was asking me. So that also definitely I'll discuss when I'm discussing about the RCB model. Anything else? Any, like you want you have, if you have any issues installing, or if you have anything, you can always message in the group. Uh, I hope you are all in the group, right? Whoever, I think, yeah, you should be in the group because otherwise you will not get the link, right? Yeah. So if no one is having any questions or any queries, JP sir, I think I am almost done with my presentation for today. So
Uh,
yeah, if you have
any
anything, you can.
questions from students end? Any questions? So I think no one is responding means we take it as a call. There are no questions.
Sure.
So thank you very much, Prithvi sir, for your knowledge. I mean, sharing the knowledge to our students. So hopefully, the tomorrow all the students will uh, come prepared with the installation, and will begin from tomorrow onwards.
Sure.
Actual training. Thank you
Okay,
very
sir.
much, sir.
Yeah. Thank you.
Thank you,
Thank you,
all the
JP sir.
students.
Thank you, students. Fine. Thank you. Bye.
Bye.